So there are quantum neural networks in the research community already, right? So let's talk about the basic idea behind it, right? So what happens is that in the normal neural network, you have the neurons, right, or the perceptrons, which are taking the inputs and processing output based on the activation function. In the quantum neural networks, what you have is actually a rotation gauge, which is based on the theta, right, the particular angle on which it is actually rotated. What happens is that the input qubit actually comes, the rotation actually happens to the particular qubit, and the output actually produces. So what actually is learned, the learnable parameter is nothing but this particular theta, which is the angle which is actually being rotated, right? So what happens if you actually just compare the performance of these particular two neural networks? It has been found that they are mostly similar, because the thing is that it is just a different formulation. If you actually just try to visualize, it is just a different formulation of the same neural network, right? You're just trying to optimize the particular theta or the learnable parameters, right, which are actually just there also, that in the form of w, that's weights, and biases, right? But here you have those particular angles, right? But the benefit actually comes when you are actually including the principles such as superposition and entanglement into these quantum neural networks. What if you actually just entangle two particular qubits, right, which are coming as input to the particular neural networks? Now it actually becomes different. What happens is that whenever one particular qubit actually goes to a particular state and then collapses, then the other qubit will be influenced in the similar fashion, right? Whatever the collapse is there. So these actually gives you an immense benefit of actually having more computation power than the traditional neural networks.